Okay, thank you very much for the introduction. Good. So, EDA on the cloud. I mean, how do we actually get? I mean, it's great to see kind of this infrastructure alley where a lot of people are really starting to get interested in running EDA on cloud. What I would really kind of like to convince you of this afternoon, that just lifting workload from one machine to another, or from your internal data center to another data center, that's not really what's going to make or break EDA in the cloud. And what we experienced in IBM, what is really going to be a game changer, when you can not just talk about capacity, but really talk about capability. Talk about a completely different design experience where people are starting to build chips a very different way. So let me tell you a little bit how I got into this. So exactly 5 years ago, exactly on this DAC floor, just a little bit upstairs, I was being asked to predict what's going to happen in the next 25 years of electronic design automation. So I went at it three ways. One, I interviewed a lot of DAC entities. I asked a lot of our internal designers, and I read this report from Brayton and Kong and so on. And they all pointed not that they needed so much better tools, they really needed a better design experience. Simplified, standardized, scalable, predictable design flows. Yeah. Designer said, I want to get to my data anytime, anywhere, from any place. I want to analyze my data with whatever tools I can lay my hand on. So they just don't want to run tools and then write thousands of lines of scripts to extract some key pieces of data. He said, I just want it to look like Google Maps. Right? It should not be any harder to find the critical path in your chip than finding the critical path from here to San Francisco Airport at any time of the day. Right? Why can we, I mean, if you're on Google Maps, there's just a slider which says, hey, give me the traffic tonight. And it tries to predict it based on the traffic on Tuesday nights, or Monday nights, a week ago or 2 weeks ago. You can get real-time traffic. You can get anything in between. Is the data ultimately reliable? No. Is it close to reliable? Yes. But the data is there all the time, every second you need it. So when I got back to IBM 5 years ago, I basically took my engineering team together. I said, hey, how can we go build something like this? So today we'll show you a little bit sort of how we got there. The most exciting stuff is going to be at the end when Kareem, who is the lead engineer on our timing tool, actually going to tell you how we did timing in this type of environment. I'll talk to you a little bit what we are designing, what our infrastructure is on which we have built this, and then Kareem will kind of give you some of the detailed examples here. So what are we building? Yeah? In IBM, we are building big Z processors for our mainframes. These are the large computers that still run a good part of the financial industry, the insurance industry, most of the governments, most of the airlines, extremely high transactional, huge systems. And if you see the evolution, most of the time we got a good boost out of technology. But if you look at the more recent generations, especially the last one, most is coming out of microarchitecture, like new microarchitecture, new accelerators that are embedded in the chip. A lot of optimization and branch prediction, pipeline optimizations, correct? It's not so much coming from the speed from the next technology node. So this puts a lot more stress on the EDA environment, on the EDA tools to actually deliver new function, for them to way more quickly explore some of the implications of really major design decisions on what it's actually going to mean on their chip. Right? So they really need full analysis capability all the time, every day, to make very large-scale type of decisions and have pretty good understanding where that ends up on the chip. The other processors that we are building is basically our Power 9 processors. I don't know, who saw the Supercomputer 500 top ranking being published this morning? Okay, there's maybe 3 of us. So the good news is for us in the US is on top. The better news for IBM is it's based on this Power 9 machine that we have built using some of the tools that I will show you. Also, if you're interested, right there's one of the drawers out of one of the machines right at the IBM booth, the first one on your right there. There you can see kind of one of the drawers of the big Summit supercomputer that has been built at the Oak Ridge National Laboratory. So kind of what type of design environment do we have that allows us to build these type of machines, and how did we take that and really build that into the design environment that really gives you the new cloud-based design experience. So first, let me tell you a little bit about our kind of overall verification type of workload. Yeah? I mean, one of the fun parts that we had, if you look at these two machines, these two sites, these were previous generations of these supercomputers. They are a little bit older generation that we were lucky enough actually to get back in IBM. We could lay our hands on, actually use for our internal workloads to kind of to design our next generations. So that gave us access to a pretty large number of cores, actually to run ridiculously large number of jobs on. Yeah, overall, good number of servers, pretty ridiculous amount of data. We collect about 1.5 terabyte of coverage data every day from all our functional simulations. And are pretty much able to fill up our compute capacity to 85-90 type of percent capability. So this is the logic verification type of workload. Yeah, if you look at the design implementation, we run about a little over 16 million tool runs. So this is mostly digital implementation, timing analysis, power analysis, noise analysis, DRC checking type of runs. We have about 15 terabytes of physical data for a particular chip tape out. And you kind of see some of the other statistics here. So our challenge was that we had this environment, correct? But how do we take this environment and move that to a cloud-based environment, while basically keeping on operating? It's really how are we going to change the tires while our designers are actually continuously pushing out chips while we are going. So what we did is basically we said, okay, which workloads can we take and lift and shift from one environment into a cloud-based type of environment? How can we take them, take key APIs, expose them to the analytics and machine learning type of capabilities? After that, how do we refactor some of the code, correct? These big monolithic EDA applications, refactor them and build them into smaller services that can basically give you the right answer at the right time for a particular type of queries. And that gave us a really nice base to build a lot of analytics capability, and we have started to build some really nice machine learning capability on top of that. So to be able to do this shifting and lifting, we were lucky to have our hands on a good amount of IBM technology. So most of our traditional computation is running on LSF Spectrum, which is basically the traditional workload management for all the heavy-duty compute in most of the EDA infrastructure. But we get pretty good virtualization for containerized workloads, for big data, and all the way to machine learning, through some of the key abstractions that IBM Spectrum Computing actually provides to us, so we don't have to worry too much on everything that's sitting there in the underlying hardware. So let me give you kind of one example how we took our digital implementation flow and kind of started to turn it on its side, and kind of, instead of running everything as one big monolithic set of jobs here, kind of started to distribute it over this environment, kind of to create that type of analytics type of capability. So if you look at your traditional digital implementation tool flow, you have a whole bunch of optimizations engines, synthesis, placement, routing. You have a lot of analysis tools. They talk together to a backbone database where we use open access. I talked about that this morning, with a bunch of APIs to put all these pieces together. So we didn't want to touch this too much at the start, right? Because as I said, we have a huge environment that's running, producing data every day and every minute. So we started to kind of supplement this with some other key data structures. One for DD, for design data, which is basically a very fast read-only data structure for all your netlist, all your physical data, down to individual shapes, all the way from the netlist. And we supplemented it with a graph database for basically all the graph-based type of operations that you want to do. I think mostly timing analysis, and you'll see some great examples of that later. So that became a very nice trove of basically analytics information that we could start to feed to our designers in a more intuitive manner and in a way more continuous manner. Okay? The great thing is these jobs, they basically run all the time as huge batch jobs, produce data that we continuously ingest, consolidate it, and then kind of make it available at the outset. Yeah, at the same time, we started to provide some REST APIs to some of the key analysis tools. Okay. So what does that allow us? That allows us basically to consider this as a live model as well. Okay. So in addition to the derived data that we have here, we can leave these big sessions up and running, but again, access their information from a web browser type of environment through the REST APIs that we kind of architectured in there. Then designer takes that information, and we gave him some powerful mechanisms kind of to orchestrate the environment and says, hey, I would like to run these jobs again with these parameters, try to get us better power, tune me this way, tune me the other way. And we're kind of starting to use the same infrastructure to put machine learning on top, using this as the big data troves, and instead of putting the human in the loop here, basically let the machine learning do some of the orchestration and basically give more preference to better scenarios, or in the verification flow, basically run more of the tests that provide better coverage and things like this. Relatively easy machine learning jobs that significantly can cut down the number of meaningless jobs that you would run otherwise on this site anyway. So then we took this and we mapped that kind of to the Spectrum infrastructure that I showed you on one of the earlier charts. So all the high performance computing jobs, they just keep on running on this site, pretty much untouched, except for the APIs here and a little bit of the orchestration to kick off the jobs. We started to run these as basically services, so services that are always up and running and the analytics tools can query. And we started to use some of the machine learning infrastructure, basically run some of the machine learning on top of it. The nice thing is that this can basically run inside your compute farm, using the different layers of virtualization of all the compute that you have. In addition, we kind of had to take some very complex tools that people kind of depend on and make them the kind of client-server architecture as well. So let me give you kind of one example of a tool that we are using, which is basically in the front-end verification flow. It's basically a tool that does source-level debug, get you all your verification traces, lines them up with your coverage data, and so on, which used to be one monolithic tool. So we took that, we broke that into two pieces. Basically, one piece that was going to run in your web browser, which is really the client architecture, and the other part which really became the server of the server data architecture, which kind of serves up all the key elements that you want to query about your design. So once we had broken that up, we kind of could evolve each of the sites. We could take the core of what we call the Nexa Mantis engine and really make that the data server that runs on the server side of the farm. And then we could take basically the client side and basically replace that with tools based on all modern web technology that basically just runs in your browser and talks to the server side through a bunch of the web-based APIs here. So this became actually incredibly powerful because we get the concept of sessions. Okay? This is more or less stateless. This basically maintains all the state that you have about particular design. So it becomes extremely powerful actually for designers to collaborate and work together. So particularly, which people design logic here? Nobody. Oh, the people back. Who debugs logic? So if you're debugging logic, the problem is you have 12 different bugs that you're kind of debugging at the same time. You fix one, you send out a couple of 100 jobs, and a few hours later, kind of, you need to go and look back. Hey, did this actually fix my bug? Right? So what this allows is basically all these sessions you can keep up running. Your debugger is at the right point in time. You have the right source codes loaded, the old and the new version. You can compare old and new, and you can basically bring the session back up as soon as the whole batch of simulations that you kicked off are done. So while you kick it off, you move to the next one, the next one, the next one, and you can actually address like 10 bugs in parallel, while in the background, the rest of your verification is running. So our designers absolutely love this. Because it really gives them a very different experience of dealing with their verification data than they were used to. In addition, what this gave us the ability basically not only to pause and resume the sessions for yourself, but just delegate them to somebody else. Because it's a simple web pointer that you can hand to anybody, yeah? And they can pick up your debug session with full state preserved for everything that you need to basically bring up that session. In addition, we allowed basically for stickies to be attached to all different parts of the job, and you basically can hand that to somebody else and say, hey, please look at this, please look at that, here's the session, has everything ready for you. So the key message here is really, running on cloud is nice because you can get a lot of work done. But what really started to tilt things over is when you get a very different design experience, yeah, in your designers, in your logic designers. They really start to love it and say, hey, this is really a different way of designing. Instead of individual tools, I'm basically running a big data farm and looking at the data that is on my design and kind of make step-by-step progress. So I only talked very, very shortly about kind of what we're doing in the verification environment. Yeah, there were not too many logic and verification engineers here, but if you're interested, on Wednesday we'll have another session upstairs in building 307, where we'll talk a little bit more about functional verification. And now I would really like to hand it over to Kareem for the most exciting part, where he will show you kind of how we do timing debug on the physical timing side of this environment.
Great.
Take it away, Kareem.
Thank you very much, Leon. Can everybody hear me? Microphone working okay? Okay, let's see if this thing works. If I do that, what will happen next? Perfect. So I'd like to talk a little bit about how we feed the beast for analytics and machine learning. And I really want to get out of the business of chasing our data all over the place, spending a lot of time chasing data, and I want to be in the business of doing interesting things with our data. So as Leon mentioned, I'm a timing engineer, so why do I chase data? What are the situations that lead to that? Well, number one, in the realm of physical design, and certainly in timing analysis, we love divide and conquer strategies, right? We love to take our large monolithic chip and break it up into dozens, if not hundreds, of individual components and send this component here and that component there and that component over there. That's how we get reasonable turnaround time to analyze billions and billions of transistors, right? The problem is, with this divide and conquer approach, we have data that's spread out all over the place. We have to put that back together. The second challenge, the second reason why we end up chasing data, really has to do with persistence. And the question is there something more intelligent we can do when our timing, our noise, or our power analysis completes, other than writing out a simple, static, text-based report that looks much like the reports when I joined IBM 20 years ago? There's got to be something better. And so the vision here really is that we want to have access to all of our data at any time across the hierarchy in a very easy to manage fashion. And so the way we've done this in the realm of timing analysis is we build a self-consistent, unified, persistent graph database model which represents the timing analysis results across our complete microprocessor hierarchy. This is all running on our IBM Power 8 cloud, all orchestrated by LSF. And this is a really, really powerful model for us. So I'm going to shift to the next page and just explain a little bit what this ecosystem looks like. So in the top portion of this chart, we have our traditional C++ tools, which are running distributed across the cloud. We have our Einz timer, our Einz noise, our Einz power analysis runs, all of which are being executed on our LSF Power 8 cloud. Those jobs are being continuously monitored and produce all kinds of very interesting graph-based data in the realm of timing analysis. Our monitoring and orchestration services observe every time a job completes and the data is promoted. Whenever a designer says this particular job is blessed, that event gets recorded in our registries. All of the data is automatically ingested then in a completely self-consistent, hierarchical timing database. And so we have registries that keep track of where are all of the graphs, where are my latest timing results from today, Where are those results from last week? Where are those results from last month? So we can do the types of trend-based analysis that my boss was just referring to a few minutes ago. So now this opens up some really, really interesting use models and experiences. So how many folks out there do work in timing, power, or noise analysis? Where are my timing engineers? Okay, so we have a few of them in the audience. So the very first question, this sounds like something really simple. Across the entire microprocessor hierarchy, tell me where and what are my worst end latch-to-latch paths. Sounds really simple, right? The problem is that if all you have to work with are simple text-based reports, you have to search through a ridiculous amount of hundreds of text-based reports that are stored across the complete hierarchy to try to find this information. And you spend a lot of time writing Perl and Python scripts to go chase the data, find the reports that go along with the version of the microprocessor design that you care about today, parse that data. This is a really, really painful process. Now that we have all of our timing information in a single, self-consistent, hierarchical graph database, this is ridiculously easy. Our engineers now write one line of code which executes in 1 second across hundreds of millions of nodes and returns the answer to you. So much less time spent chasing the data means more time that we can spend analyzing and machine learning and doing really interesting and cool things with our data. So here's another example. Instead of a single latch-to-latch path, supposing I want to expand that out. I want to trace a critical path through n stages of latching, right? It's a very common thing that we need to do in the timing analysis space. Again, if you have text-based reports and your data is spread out all over the place, this is ridiculously complicated. A lot of parsing, a lot of really painful Python code. Most of our timing engineers up until this point probably would not attempt to do this type of analysis. Again, a completely new experience is available to us now. We have all of our timing information in a graph database. Remember, that means that we have captured every single path. We miss absolutely nothing. And so if we want to trace through multiple stages of latching, this is a very simple one-line program that executes in a second or so. So now instead of a single latch-to-latch path tracing through multiple stages of latching, supposing I want to do some interesting analytics and machine learning on an entire fan-in and fan-out cone. I've observed that I have a critical net with a failing timing slack, and I want to know something about the entire cone of logic that my critical net feeds, or the entire cone of logic coming in and feeding my critical nets, because I want to do some interesting analytics and machine learning on that profile. Well, this is virtually impossible if you have to trace through simple text-based reports, right? So now, again, since we have all of the data nicely organized in a self-consistent database, this becomes ridiculously simple. Give me a net that you're interested in, and with one line of code, which you see here in gray, we can find all of the fan-in latches, all of the fan-out latches, and I can tell you anything you want to know about the timing of those latches or any logic in that entire fan-in and fan-out cone. So I kind of have an interesting story. I was collaborating with one of the lead timing engineers for our Z microprocessor system. And he was lamenting to me. He said, you know, Kareem, I'm going to be very busy in the next few weeks. I have to write this complicated script to analyze our timing constraints. Every component that we analyze has a set of input constraints and output constraints, and they have to be optimized to make sure that we can converge on our design point quickly. If you don't do that properly, you can't converge on the right design point. And so my friend was lamenting that this process of just gathering all of the data to analyze timing constraints across dozens of macros, dozens of components, was going to take him 6 weeks just to gather the data, let alone do anything interesting with it. We sat down, I showed him how we have all of his data cataloged and organized and traversable in a graph database. We sat down in 5 minutes. We wrote one line of code, which executed across the entire microprocessor hierarchy, found every single component that my friend was interested in, found every input, every output of that component, ran the analysis that he cared about, got a useful result in 5 seconds. So that's how we deliver a different experience. We go from 6 weeks to write the code, to just gather the data, to forget about all of that. I've got you your data in 5 seconds. Now please spend the next 6 weeks analyzing the data and doing interesting, high-value activities. So of course we have all of this integrated in a very nice, in a couple of very nice frameworks, one of which is Jupyter Notebooks. So we have, in addition to direct database APIs that you can call over the web, we have a lot of engineers who do like to write scripts, and we have a library of Jupyter Notebooks that are available for our design engineers, so they can perform many of these common queries just by calling a single Jupyter or a single Python function. And then we can make use of data frames, all kinds of interesting charting and plotting capabilities. We also have a web-based portal that gives us access to all of our timing database information. So you can either get access to our Neo4j timing graphs from today, yesterday, last week, last month. You can compare results between today and any point in time. Or you can get direct access to your latest and greatest live Einsteimer session if you want to check on the progress of your latest timing run. And all of that information is available in a very simple point-and-click interface. So you can get a high-level summary, for example. You can ask questions from an integration standpoint. What are my most critical cross-hierarchy failing timing paths? And you can also do dive deep types of analysis and really poke at each of your critical paths, look at a detailed set of timing information, and decide, how does this path need to be solved? Is this an integration problem? Do I need to give this to an integrator? Is this a logic problem? Do we need to go back to logic design? Is there a constraint problem? And so right here on the web, you can just go in and type, I think this is a logic problem. This particular path needs to go to my friends in the logic design team. Or I think this is a constraint problem. So-and-so, please go ahead and update your timing constraints so that we can resynthesize this path properly. So I think I'm just going to wrap up my mini section by saying that I'm a very big fan of spending much less time chasing your data and much more of our valuable time doing interesting machine learning and analytics. And I think we've come up with some pretty cool ways of doing that. So what do you think, Leo?
Yep. So maybe let me try to kind of summarize and kind of bring all the pieces back together. Yeah, I think one is that we had the kind of realization that EDA tools basically need to run, they produce data. Like in a big design project with hundreds of engineers, data is always moving. Yeah? And instead of taking that as an excuse why you cannot do certain kind of things in EDA, we took that kind of as a virtue. We said, okay, the data will always be moving. Yeah? But as long as we kind of driving to a convergence point and make sure that the designers have a coherent, consistent view or slice through the data at a particular point in time, it's okay. It's okay. It's okay that you have yesterday's timing report if today's job just didn't finish when you came in the morning. It's a lot better than nothing and just waiting till it finishes till 4 or 5 p.m. And, because there's more stuff for him or her to be done. The same thing, logic bugs, there are always more, correct? There's never a shortage of them. You just need to serve them up and get the highest priority ones queued up and kick off the next runs that provide the best coverage. So we basically really decoupled the EDA tools. Okay, EDA tools are just data generators. They just generate massive amount of data, let them do what they do, and we need to orchestrate, make sure that they spend their compute cycles the most efficient. Not like ultimately efficient, but most efficient. And there is some noise in the process, but that's okay, because the worst you do, you run a couple of jobs that don't go anywhere. Yeah? And that burns some licenses, but if you have enough of them, or yeah, then that is not your major headache. And luckily in IBM, we don't have that. Yeah. So The next part is, okay, if we then can take and try to use modern web visualization to really make it a lot more appealing for the designers actually to interact with their data. And there, I mean, we are just kind of at the beginning of that avenue because it's very experience-based, so we are trying to work with a lot of leading designers and say, what do you actually want to see, correct? And kind of quickly iterate what they actually want to see on their screen and how to kind of best use the real estate that they have available to them to kind of to get to the most meaningful information, which is probably actually more complex task than the whole data management task. Like the whole data management, you can kind of figure out version, a lot of good engineers can do the job. I think the user experience, we are just starting and learning our way through it, what people actually want to see and what's the most effective way to serve up all this data. But the good thing is there's so many frameworks out there that all these web development companies have put out there that it's pretty easy to, once you have decoupled the data, to plug in a couple of other tools or paradigms. Hey, do you like this? Is this what you're looking for? Okay, let's connect it in there because everything runs in your web browser. So I think what we have seen at the first few steps is that we get our designers to be able to focus more on the new type of logics, the new stuff that they actually need to put into their design process and get a quicker idea of the design implications. We are starting to provide them more and more design insights. And at the same time, we came up with a kind of a tool architecture that maps much better to big client-server EDA clouds. And I think I'm seeing good excitement in people who are getting a different experience and not just getting more jobs that we can push through the system out there. With that, we are happy to take any questions. And is there a microphone? Let's wait for the microphone to come from the back here. You want to grab it, Kareem? Or?
Sure.
Because there's nobody, or there's this gentleman there. I think otherwise we...
Hi. I want to ask, you mentioned that the designer, if they want to look at some data, say for example, they have a 100 timing report, and then they want to look at one of them and then pass the colleague, and the data will be live. So are you going to keep like 100 concurrent sections, your timing sections, so that it can pass over to your colleague to review? And the second question is,
to a first order, the answer is yes.
Okay.
Yeah, and of course, eventually we need to retire things. Yeah, and we have found that 2 weeks is probably a good time slot where people where things start to age out. Yeah, so we keep bigger snapshots that we keep forever, and we kind of keep like 2 weeks of data live. Yeah, which I think Kareem. Is your mic still working? He knows how many timing graphs we had running as of last week. I remember it was 8 billion timing segments or whatever you told me.
So Leon is absolutely right. 2 weeks seems to be the sweet spot in terms of our live timing graphs. I think right now we host over 20 billion timing properties on our Power 8 cloud, no problem.
Yeah.
Then it means it will need a lot of license, right?
Sorry?
Need a lot of license.
Yes. Yes.
Okay.
But yeah, we in IBM, we have some advantages. We have lots of compute. And for most of the tools, I own the licenses. So,
okay.
So that's certainly...
Yes,
that's
I
certainly,
understand, but I'm trying
yes.
to think of if we are going to use similar approach, what will be our limitation? And I think smaller companies do not have unlimited license sort of, right? So the second question...
No, yeah.
Second question is, you mentioned about that, I think it's a lot of, it seems to me that you generate a lot of data. In fact, the most innovative thing here is you have found a good way or a very effective way to collaborate all your data together and then to do a query on the data, right? So, and then you mentioned about a lot of the machine learning. Are you, like IBM have Watson, are you using the Watson AI at the back to do the machine learning?
Yeah. Okay, so a couple of parts. So one question you asked sort of, what kind of the business problem here, right? And I think what I hinted at 5 years ago at the keynote at the time, and the value is in the data. The value is, so if we can get if we can start to pay the EDA vendors for the value they provide, instead of for the number of licenses that we run, we are all better off. Right? So I think there is a business model actually where they can give you 10,000 licenses and you only pay for runs that in the end are actually valuable to you. So you pay more for kind of the quality of the data that comes out there, one part. So then the next part, kind of, I mean, IBM, yeah, the other advantage, we have a very rich capability of AI offerings. Yeah? So as we are in the initial stages there, we have done a lot of good work in the functional verification area, especially in coverage data and sifting through that. And we have the capabilities kind of to hook up some of the machine learning frameworks that we have in IBM to our basically EDA infrastructure and use that to our benefit. On the physical side, physical implementation side, we are kind of just starting. So we don't have too many really good results there yet. I mean, we have a tool called SynTune-Sys, yeah, which uses some kind of genetic algorithm kind of to sort scenarios that you run in your physical implementation flow. And we have seen some interesting results that say, hey, if you run enough of them with the right mutations, you can significantly lower the power and not sacrifice your timing, for example. So we are seeing some interesting, and we had a paper in the IBM Research Journal, I think 2 years ago or so. So we're starting to see some small parts where you start to really even can drive a huge design flow and start to get benefit out of this. But I think we are just at the tip of the iceberg here. Yeah, so it's pretty exciting time. I think that's going to start now that we have actually starting to have enough data to actually start to learn from.
I have a very simple question. So maybe you already answered my question. So in the model you just presented, any third-party EDA software involved, like Cadence, Synopsys, or any third-party cloud vendor involved in this, or totally owned by IBM?
So, so we have a mix of our own tools and various vendor tools. We heavily rely on OA as the SI2 OA database, kind of as the backbone. So tools that play well with OA can plug well into our kind of physical part of the design flow. On the other part, we have not ventured outside the IBM cloud. Yeah. The infrastructure sort of supports that, yeah, but we have no need to do that yet. But that's certainly something we will be looking at in the future. In the front here.
You mentioned licensing based on the value. Who determines the value?
That's a good question. The value in the end is basically what the designer or the verification engineer gets out of it. Yeah. The question is, how do you value the value? That's, yeah, that's another interesting question. Yeah. And I think there are some interesting, there are a lot of interesting business problems that are going to be sorted out in the EDA industry in the next 5 years. Right? The first is basically, we're getting this whole machine learning paradigm. Okay, who owns the data? You as a design engineer, you as the verification engineer, you're the logic designer? Probably yes, correct? Now we're going to build machine learning models on top of this data. Who owns the models? You, the EDA vendor? I don't know. Then who can do something with these models? Can you take these models and sell them to somebody else who can then optimize, so your competitor who can optimize his design with your learning? That's the kind of interesting discussions we're going to get into. Yeah. In addition, that the license-based model doesn't work anymore in the cloud era, right? The cloud era is compute is so dirt cheap. I mean, it costs probably like 1/10 or 1/20th of a compute cycle to buy the IT than to put the EDA license on top of this. Right? So that's totally out of whack. If your major paradigm is to produce as much data as you can and try to make sense out of it. So somehow I think that value needs to adjust. Machine learning is going to drive an interesting part of these discussions, who value and who prices the data and the models. And hopefully a derivative of that discussion is, if I want more data and produce more data to make better models, do I have to pay for every license to do that? So I think there's some trade to be had on both sides. And it's very interesting to see how the business model will evolve. Again, I predict in the next 5 years, more evolution in this side than we have had in the last 35 years, where we only moved from perpetual to time-based licenses, and pretty much nothing else has happened. But I'm very interested in other people's opinions on this, because yeah, it's going to be interesting how that is going to play out in addition to the technical side of things. Okay. Okay, thank you all very much for coming. As I said on Wednesday, in the middle of the afternoon, in the IBM forum upstairs, we'll talk more about verification environment. I think you can still register probably in the IBM booth for that event. And you'll find our names on the IBM DAC webpage, also on the DAC web pages if you need any more information. Okay, thank you.
Great. Thank you.